Good day everyone, welcome to my channel. So today I'm gonna show you how to solve problems involving center of gravity or the centroid, parallel axis theorem, product of inertia, composite area, and the mass moment area. First, we have this problem for the centroid of the gravity. Determine the coordinate of the center of gravity of the object shown in the figure above. So we have this. So first, we're gonna solve for the area. We have this area for part 1, area for part 2, and area for part 3. So in this object, this is the area for the part 1 with the dimension of 3 by 9 area. This is the part 2, dimension of 3 by 4, and the area for part 3, 3 times 9 by 3. So to solve this, we have the area for part 1, 9 times 6, 27 centimeters squared. In the area for the part 2, we have the 3 centimeter by 4 centimeter, we have 12 centimeters squared. In the area for part 3, we have the dimensions 9 by 3, 27 centimeters squared. Just gonna put it here. And next, we have to solve for the center point lies on the x-axis, x and y-axis for part 1. We have this. We have to look at the coordinate or the center where the coordinate where the center for the part 1, the x and y-axis lies. So for the x-axis, we have this. X is equals to x1 is 1/2 of the 3 centimeters. We have 1.5 centimeter. The x2, we have I'm sorry. The y1, we have 1/2 of 9 centimeter. It's probably be here. 9 centimeter. So we have 4.5 centimeters. So it's gonna put it here. 1.5 centimeter, 4.5 centimeters. For area for the part 2, x2 is equals to 3. That is 3 plus 1/2 of 4 centimeters. So this is 5 centimeters. So to solve for the y coordinate of the area of the part 2, we have to add this 3. This is probably here since the length is 9. And we have 3 centimeters, 3 centimeters. So this is probably 3 centimeters. So 3 plus 1/2 of the 3 centimeters. So we have 4.5 centimeters. Next, for area of the part 3, we have this 9, still 9 by 3. So for the x of 3, we have this 3 plus 4 plus 1/2 of 1/2 1/2 of 3 centimeters. So we have this 8.5, and the y for part 3, we have this the half of the 9 centimeters. So this is probably 4.5 centimeters, 8.5. And now to the next one we do is to get the coordinate of the center of the gravity that lies for the x-axis. And the y-axis, we have this formula: x is equals to x1 times a1 plus x2 times a2 plus x3 times a3 divided by a1 plus a2 plus a3. Same here for the y-axis. y1 times a1 plus y2 times a2 plus y2 times a3 divided by a1 plus a2 plus a3. So let's solve for the x coordinate of the center of the gravity. Have this, so 330 centimeter cubed over 66 centimeters squared. 330 divided by 66 is 5 centimeter. Next we have y1. And since we have now the x and y axis, so our centroid is at 4.5. So next we're going to solve a problem related to composite area using the parallel axis theorem, and this can be used to find the moment of inertia of an area. So we have this formula, ix and the iy. This is the moment of inertia. Formula for moment of inertia along the x-axis. We have this one. So next, we have this problem. Determine the moments of inertia for the cross-sectional area of the member shown in figure below about the x and y centroidal axis. The three sections can be divided into three rectangular areas. We have this A, this B, and this C. So, and the centroid is located here, D. The moment of inertia about its centroid axis is this one. Since this is the rectangular areas, we have this one over 12 base times height cube. And showing the diagram of all the measurements, we have this one. So for the we're going to use this one, and then using the parallel axis theorem for the rectangles. The calculations are as follows. We have these rectangles A and C. Since they have the same dimension, this one A and C, 400 and 200 as the width. So to solve for the moment of inertia along the x-axis, we have this formula. And we're going to solve this one. 1 over 12 times 200 millimeters, the base, and the height cube 400 millimeter cube, plus the area 400 times 200 times the dy, which is the 600 millimeters. The measurement from the centroid of rectangular A to C, we have the 600 squared. So we have this 2.99 times 10 to the power of 10. So next we're going to solve for the moment of inertia along the y. We have this formula. 1 over 12 times the base, which is 400 millimeters, and the height, which is t, 200 millimeter cube, plus the area 200 times 400 times 700 millimeters squared. So we have this result 3.95 times 10 millimeter to the fourth. So we have millimeter to the fourth. So next for the rectangle B, I'm going to use this formula Ix as 1/2 base times height cube. We have this 1/2 times base. Our base is 900 millimeters times height. We have the height 200 millimeters cube. So resulting to 0.6 times 10 raised to the power of 9 millimeters to the fourth. And the Iy is equals to 1 over 12. This is 1 over 12, sorry. 1 over 12 times 200 millimeters times 900 millimeters raised to the power of 3. So we have this 1.215 times 10 raised to the power of 10 millimeter to the fourth. Since we're done, we have to solve for the Ix, the total Ix. So we have this 2 times, since we have this A and B, rectangles A and C, 2.99 times 10 raised to the power of 10 millimeter to the fourth, plus yung Ix sa rectangle B, 0.6 times 10 to the power of 9 millimeter to the fourth. So it's 6.04 times 10 raised to the power of 10 as the Ix. And the Iy is 2 times the Iy, 3.95 times 10 raised to the power of 10. Sorry, I forgot. Millimeter to the fourth. 2 times 3.95 times 10 raised to the power of 10 millimeter to the fourth, plus the Iy for the rectangle B, 1.215 times 10 raised to the power of 10 mm to the fourth, And now we have this result, 9.115 times 10 raised to the power of 10 and 4. So, have this final answer for Ix and Iy. So, next we're going to deal with the mass moment of inertia. We have this problem. The pendulum consists of two thin rods, each having a weight of 20 newtons. So, determine the pendulum's mass moment of inertia about an axis passing through the pin at point O. The moment of inertia of rod A about an axis perpendicular to the page and passing through the endpoint 0 of the rod IO is equals to 1/3 ml squared. This is also the same value with the IG is equals to 1/12 ml squared plus the parallel axis theorem. Have this md squared mass times the distance squared. So we have this I of moment of inertia of from O to A. We have this 1/12 mass times length squared plus md squared. This 1/12 our mass. So mass, since we have 20 newtons, we have to convert this one. So 20 newtons, 9.8 meters per second squared times the length. Our length is 4 meters, 20 squared plus the mass, same with this 20 newtons over 9.8 meter per second squared times the distance. We have the 2 meters squared. The result we're going to calculate using the calculator. 20 divided by 9.8 divided by 12 times 4 squared plus 20 newton divided by 9.8 times the 2 meters squared. You have this 10.88 kilograms, since this is now a kilogram meters squared. For rod BC, have this moment of inertia at O is equals to 1/12 ml squared plus md squared. 1/12 times 20 newton divided by 9.8 to get the mass times the length. We have 4 meters squared plus 20 over 9.8 meter per second squared times the distance squared. This is so we're going to calculate this one. 20 divided by 9.8 divided by 12 times 4 squared plus 20 divided by 9.8 times 4 squared. Sorry. Ulit. 20.8 divided by 12 times 4 squared plus 20 divided by 9.8 times 4 squared. We have 35.37 kilogram squared. So, since we have now these values, what we will do next is to add the two to get the mass moment of inertia. So mass moment of inertia at O is equals to 10.88 kilogram meter squared plus 35.37 kilogram meter squared. We have 10.88 plus 35.37. We have 46.25 kilogram meter squared. So our mass moment of inertia about an axis passing through the pin at point O is 46.25 kilogram meter squared. So next we are going to deal with the product of inertia of the area. So we have this problem. Determine the product of inertia for the cross-sectional area of the members shown about the x and y centroidal axis. We have this one product, same as the old problem given, and this is the diagram for the measurements that given in this figure. And the cross section can be subdivided into three composite rectangular areas, the A, this B, and the C. Due to symmetry, the product of inertia of each rectangle is 0 about a set of x and y axis that passes through the centroid of each rectangle. So using the parallel theorem, we have this one. For rectangle A, we have this formula. Since the product of inertia of each rectangle is 0, so this is 0 plus the area of rectangle 1, A1, so 400 times 200 dx as negative 700 times the dy, which is the 600 millimeter, equals to, I'm going to calculate this one, 400 times 200 times 700 times 600 is negative 3.36 times 10 raised to the power of 10 millimeter to the fourth. And next one, for the rectangle B, 0 plus area, which is 200 times 900 times 0 times 0, so this is already 0. And the rectangle C, for the rectangle C, so this is 0 plus the area, we have this area 400 times 200, and the dx is 700 times the dy negative 600. So this is negative 3.36 times 10 raised to the power of 10 mm to the fourth. And the product of inertia for the entire cross section is Ixy is equals to negative 3.36 times 10 raised to the power of 10 mm to the fourth plus the rectangle B, which is 0, that one, plus negative 3.36 times 10 power of 10 for the rectangle C. So to sum it up, we have negative 6.72 times 10 raised to the power of 10 mm fourth. So we have our product of inertia for this problem as negative 6.72 times 10 raised to the power of 10 mm fourth.